Hi there, welcome to this short vodcast on physics and physical measurement, which is the first unit in the IB Diploma Physics course, specifically the topic the realm of physics. Now what the realm of physics is really about is looking at devices and values which are at the extremes of the universe. So we're looking for the range of magnitudes of quantities in our universe, from the very smallest things to the very biggest things. So we're looking for that range. To do that we may have to do a little bit of recapping. So let's first of all recap on how we can show very, very large numbers effectively. And we use standard form, or in Britain this will be known as scientific notation. Now, in this form, if I had a number, let's say 5326.6, to be shown in scientific notation, what I do is first of all find a value between 0 and 10, and then I show that as all of the digits, and then I extract the multiple factor. So it's times 10 to the power of something. So in this case we see we've got 5.3266 times 10 to the 3, because 10 to the 3 is 1,000, and 5.3266 times 1,000 is equal to the number which I'm looking for. So this is scientific notation, an effective way of showing very, very big numbers. So think about the range of magnitudes here. We need to be able to express quantities to the nearest order of magnitude. So that means that the digits at the beginning of this case aren't really that important, just because of the scale of the numbers we're talking about. So you normally say to the nearest times 10 to the something, rather than giving specific values. A good example here, and I've stolen this from Bill Bryson and his excellent book. He says of orders of magnitude, scientists believe they can look back to 10 to the minus 43 seconds after the moment of creation, when the universe was still so small that you would need a microscope to find it. We mustn't swoon over extraordinary numbers that comes before us, but it is perhaps worth latching onto one from time to time, just to remind us of their ungraspable and amazing breadth. Thus, 10 to the minus 43, we must remember, is 0 point, and then all of those 43 zeros 1, or 1/10 million trillion trillionth of a second. So what we're trying to say here is that these values are in the extremes, often only be given as an order of magnitude just because of their smallness or sometimes their greatness. So let's work on this. There are certain values that you must know. Okay, so certain orders of magnitude that you must be aware of. The diploma course has very little retention. It's a lot of problem solving, but this is one of those things which you are going to have to remember. So I'm just going to go through these things briefly, and hopefully you'll familiarise them yourself with this content over the course. The smallest distance in the universe is 10 to the minus 15 meters, and it is the radius of a proton or a neutron. Whilst the largest distance in the universe is the size of the universe, which is thought to be 10 to the 25 meters. The smallest mass in the universe is that of an electron, which is 10 to the minus 30 kilograms, whilst the largest mass in the universe is obviously the universe itself, which is thought to be 10 to the 50 kilograms of mass. The smallest amount of time is actually the time it takes for light to pass across a nucleus, and that's 10 to the minus 23 seconds. And the largest amount of time is the age of the universe itself, which is thought to be 10 to the 18 seconds. Now these are things you are going to have to memorise. They often come up on paper 1, which is a multiple choice paper, which you're going to do at the end of this course. Not only are you going to have to memorise it, quite often you have to manipulate it. So there's an additional feature here. Often you have to find the ratios of 2 orders of magnitude. I'll give an example here. So, to find these ratios, what you have to do is, let's say the hydrogen atom has a diameter of 10 to the minus 10 meters. Whereas a nucleus has a diameter of 10 to the minus 15 meters. So if I find the ratio of these two, I find out the difference here is 10 to the 5. So that means there's 5 orders of magnitude, and that would be the value which I'd give as the difference of these two things. So if I find that ratio, and often, as you can see here, the difference is 10 to the 5, and what I have to do is I think of the minus 10 minus 15 gives me a value of 5. So 10 to the 5 difference. Let's go through a couple of examples. The rest mass of a proton is 1.67 times 10 to the minus 27 kilograms. The rest mass of an electron is 9.1 times 10 to the minus 31 kilograms. How many orders of magnitude bigger is the mass of the proton than the electron? So please pause the video to try and answer this question. And now you've answered this question, you should have a solution which looks a little bit like this. Remembering you're only thinking about the orders of magnitude, so we've got 1 times 10 to the minus 27 and 10 times 10 to the minus 31, or 1 times 10 to the minus 30 there. So you see how we've just got it to the closest order of magnitude. One order of the magnitude is 10 to the 1, 2 orders is 10 to the 2, and so on and so on. So here the difference between 10 to the minus 27 minus 10 to the 30 is 10 to the 3, which is 3 orders of magnitude difference. Now just remember, this doesn't mean it's 3 times bigger, it means it's 1,000 times bigger. So there's a big difference. One final example before I go. A football pitch is about 100 meters long, and the distance from the Earth to the Moon is about 384 times 10 to the 6 meters. How many orders of magnitude greater is the distance to the Moon than the length of the football pitch? Pause again, try and answer. The answer should be football pitch is about 10 to the 2 meters, distance to the Moon is about 10 to the 8 meters, 10 to the 8 minus 10 to the 2 equals 10 to the 6, 6 orders of magnitude bigger. Hopefully that's given you insight into orders of magnitudes and the realm of our